Hi children, welcome to today's class. And today's first topic is total energy stored in a combination of capacitors. Okay. Actually, in the previous class, we have seen the expression for what is the total energy stored in a capacitor. Total energy stored in capacitor. Even it is not total energy stored. That is, now we are going to see that one. Already we have seen energy stored. Okay, energy stored in capacitor is given by U, that is equal to, what is that, half CV squared, that is equal to half QV. Okay, there are three: CV combination, QV combination, and what is a QC combination is also there now. That is half Q squared by C. Okay, this we have already seen. Okay, therefore, see, energy stored in the capacitor is given by this. Now, what will happen? Now we are going to see what will happen to the energy when so many capacitors are connected in series or in parallel. What will be the total energy stored? Okay, so in that combination, by that combination. So now how to do? First we will go for series combination. Okay, therefore already we have seen in series combination. See, in series combination of capacitors, okay, what will happen? See, which is constant when the capacitors are connected in series? One factor is a constant. What is that? Q. Okay, already we have seen that. Therefore, when they are connected in parallel, which is constant, potential difference across the plates of the capacitor, V is a constant, right? So now in series combination, we will see what is constant. Q. Charge, that is charge stored in each capacitor will be the same. Okay, that is Q is constant. Hope you are following. Already this concept we have seen. Okay, therefore, which means that every capacitor, there are, for example, I have C1, C2, C3, etc. up to Cn capacitors. Okay, Cn capacitors, n number of capacitors having the capacitances C1, C2, C3, etc. up to Cn. Okay, when they are actually connected in series, okay, each capacitor carries, each and every capacitor, okay, carries the same charge that is equal to Q here. Okay, now therefore what will be the total energy stored? Therefore, see, now therefore total energy stored okay by the combination, okay, stored by how many capacitors are there? N number of capacitors having capacitances C1, C2, C3, etc. up to Cn, and all are actually having the charge on each capacitor is the same. Why? Because they are connected in series. Therefore, now what is our job? To find out the total energy stored, okay, in series combination of capacitors. That is nothing but total energy. What is that? U. That is nothing but, see, we have actually three formulas: CV squared, QV, and Q squared by C. Okay, therefore now what I want is Q is constant. Okay, therefore we have to take here which formula to be used here. It is this formula, half QC combination. I don't want V here because I don't have idea about what is that potential drop across each capacitor here, but I am very sure that when they are connected in series, Q is constant. So accordingly, therefore I have to take what is a QC combination. Are you following? Therefore this is half Q squared by C, and Q is Okay, total charge. What is that? Is nothing but the charge on individual capacitors in a Q. Therefore, what is it? Half Q square. Q is constant divided by what is the total capacitance here? Series combination made this. Are you following? Total energy stored in series combination of capacitors is, what is it? U, that is equal to half Q squared by CS. Are you following? Q is the total, what is that? Charge stored in the combination. Total charge stored in the series combination is nothing but the charge in every capacitor when they are connected in series. Correct? Therefore, half Q squared by CS. Okay. Therefore, that is nothing but you take Q squared by 2, you take out. Therefore, you know very well when they are connected in series, 1 by CS is equal to 1 by C1 plus 1 by C2, etc. Therefore, it is 1 by C1 plus 1 by C2, okay, plus etc. 1 divided by Cn. Are you following? Okay. Therefore, therefore that is nothing but, okay, therefore what is that? U, that is equal to, U is equal to, okay, half Q squared by C1 plus half Q squared by C2 plus etc. half Q squared by Cn. Okay, what is that? What is that? Here, what is half Q squared by C1 here? What is half Q squared by C1? It is the energy, okay, stored in the first capacitor, that is having capacitance C1. Half Q squared by C2, it is the energy stored in the second capacitor. Correct? Therefore, very simple now. Therefore, you can say, therefore, what is that? For total energy stored is nothing but, you can say U1. What is U1? U1 is nothing but energy stored in the first capacitor plus U2 plus U3 plus etc. How many number of capacitors are there? N number. Therefore, UN. Are you following? Therefore, this is a very, very important relation. When so many capacitors are connected in series, the total energy stored in the combination is given by the sum of, very important, is equal to the sum of the energy stored in the individual capacitors. Individual capacitors. Capacitor means it is a device. Capacitance, capacity means it is a physical quantity. Okay, right. Now shall we go to the next one now? Okay, therefore, now we have to go for in parallel combination. Okay, in parallel combination of capacitors. Therefore, in next one, in parallel combination of capacitors. Okay, when so many capacitors are connected in parallel, okay, then I think you know, we have seen potential drop across the plates of every capacitor is the same. Potential difference, I am telling, potential difference between the two, what is the plates of each and every capacitor will be the same. Therefore, which is constant? V is constant. Okay, it is series combination, Q is constant. Parallel combination, V is constant. Okay, therefore, now what I want? Total energy stored. Now, next step. Therefore, total energy stored in parallel combination of capacitors. Okay, that is nothing but U is equal to, now which formula you have to use? We have three. Already told you what is it? CV combination, QV combination, QC combination. There now you cannot say Q, but this you cannot take now. Why? Because in parallel combination, charge stored in different capacitors are different. But which is constant here? V is constant. Therefore, you have to take only half CV squared formula. Is it clear? That you should know which one to be taken. Is it clear? Therefore, half. Okay. What is that? C? V squared. Therefore, what is C here? CP. Why? Because they are parallel. CP V squared. Okay. This is the total, what is the energy stored? Formula for, what is it? It is a total capacitance. And this is what is called the total potential difference. Okay. Total potential difference is nothing but potential drop across every capacitor. That is potential drop every plates of the capacitor. Okay. Potential difference. Therefore, that is nothing but, okay, V is a constant now. Therefore, you can say here half. What is CP? Capacitors are contained in C1 plus C2 plus etc. Cn V squared. Okay. Therefore, you can say U, that is equal to half C1 V squared plus half C2 V squared plus etc. half Cn V squared. Okay. What is CV squared? C1V. What is half C1 V squared? It is nothing but the energy stored in the first capacitor. And this is the energy stored in the second capacitor, and this is the nth capacitor, right? Therefore, I can write, therefore, what is U? U, that is equal to U1, energy stored in the first capacitor, plus U2 plus etc. Un. Okay, therefore, what is that? This is another plus. Okay, therefore, you can say that this is the when, okay, two or more capacitors are connected in parallel, then the total energy stored, okay, in what is that in the by all the capacitors is nothing but sum of the energy stored in the individual capacitors. So it is immaterial whether they are connected in series or parallel. The total energy is nothing but sum of the energy stored in individual capacitors. That's all. That is a conclusion, correct? Whether it is connected series or parallel, total energy stored by the combination is nothing but energy stored, sum of the energy stored by the individual capacitors. Hope you are following this. Shall we go to the next topic then? Right. What is the next topic? See. Next topic is, see, energy density. Now we are going to see energy density. Energy density of parallel plate capacitor. Okay. Now what is it? What is energy density therefore? Energy density is defined as the total energy stored per unit volume of the capacitor or condenser, whatever is that. Okay. Therefore, what is that? The energy density, okay, is nothing but of a parallel plate capacitor is defined as the total energy stored per unit volume of the capacitor. That's it. Total energy stored per unit volume of the capacitor. Therefore, energy, how to denote? Therefore, energy density. Of capacitor, okay, that is small u. Small u, okay. Energy density is nothing but what is the total energy stored by the capacitor. Total energy stored, okay. Okay. Total energy U. Total energy is capital U, no? Total energy stored divided by, whether it is not clear. Okay. Total energy, that is U, okay, divided by, what is that? Volume. Okay, volume of the capacitor. That is, what is the volume between the two plates? Okay, that is V. Okay, therefore, now what is that? That is nothing, but you can say small u, that is equal to, what is the total energy? Half CV squared. Half CV squared. What is V? V is the potential difference between the plates, and C is the what is the capacitance of the capacitor divided by, what is that, volume. See, volume, parallel plate capacitor, A is the area of the plates and D is the distance of separation that we have seen. If A is the area of the plates and D is the distance of separation between the plates, this is positive and this is negative. Is it clear? Therefore, I think what is the volume? That is AD. Correct? A. Right. Now, therefore, you can also be written as half C. What is the parallel plate capacitor? C kya hai? Epsilon naught A by D. Correct? C. Instead of C, I am writing epsilon. I am substituting epsilon naught A by D. Right. What is V? If the electric field between the plates of the capacitor is E, okay, therefore V can be written as E into D. Hope you are following. Okay, therefore this already we have seen. Therefore, what is that? E, that is nothing, electric field between the plates is given by the potential what is the potential difference between the plates is nothing but E into D. What is E? E is the electric field, okay, in between the plates, that is uniform, that is given by E. D is the distance of separation between the plates. Fine. Divided by, what is that? AD. This is a volume divided by AD. Are you following? Half, see, V squared hai na? Half, what is that? V squared. V squared means E squared D squared. Oh, okay. Half C V squared divided by AD. Okay. Therefore, that is nothing but A will get cancelled. D here one cancels. Therefore, you will be getting half epsilon naught. Okay. And what is that here? Of epsilon naught. D will, this D is also cancelling, na? Okay. Of half epsilon naught E squared, correct? Are you following? Okay. Therefore, what is it here? D squared cancels. Correct. Therefore, half epsilon naught E squared. Therefore, this is the expression for the energy density of, okay, the capacitor, parallel plate capacitor. Therefore, can you give me what is the unit of it? Unit of U. Total energy per volume है ना, joule per meter cube. Okay, and what is the dimension? These things now very dimension that you can do. Dimension of U, that is equal to energy m L squared T power minus 2 na. M L squared T power minus 2. And what is this one? Meter cube, L cube. Okay. Therefore, you will be getting this one as m L power minus 1 T power minus 2. Correct? M L power minus 1 T power minus 2. Are you following? Okay. Therefore, if you are introducing some in between the plate, if there is a dielectric, here it is in between the plates, air is there. If there is some, what is a material, a medium having dielectric constant K is there, means then what is that? What is U? U for medium. If U, it is when there is no medium or vacuum or air is there, this is the case. If there is U medium, okay, and what is the energy density of a parallel plate capacitor with some medium inside? Therefore, that is nothing but half epsilon. Half, what is that? Epsilon E squared. What is half epsilon? Half epsilon is nothing but it is half. Okay. You can say epsilon. Epsilon means what is K epsilon naught na? Therefore, K epsilon naught E squared, correct? K times it will increase, that's it. Okay, therefore half epsilon E squared. U medium is in the half epsilon E squared. What is epsilon? Epsilon is equal to epsilon r epsilon naught. Epsilon r is nothing but dielectric constant. Therefore, you can say that it is half, okay, k epsilon naught E squared. Hope you're following this one. Right. Now, next topic. Let us go to the next topic now. Next topic is, okay, common potential. Common potential. Okay. What is it? See, potential, right? What is common potential? See, for example, see, I have two capacitors, which are capacitors having capacitance C1 and C2. Okay, and I'm charging it to different potentials. Let it be V1 and V2. Okay, I have two capacitors having capacitance of C1 and C2, and they are charged to different potentials V1 and V2. Okay, so now what am I doing? I'm connecting them, connecting both the capacitors by a conducting wire and connecting. Okay, therefore, how am I connecting? I'm connecting to parallel connection. Okay, so now I'm connecting two capacitors in parallel. This is having C1 and this is capacitance, that is C2. Okay, therefore, when what will happen now is, okay, because what is that, C1, they are charged to different potentials, right? Once I connect it, what happens actually is, okay, the charge flows from the capacitor, which is at a higher potential, to the capacitor, which is at lower potential. Very important. Okay, so I have two capacitors having capacitance C1, C2, and they are charged to different potentials. Potential is different, right? And now what I am doing, I am connecting them. Okay, here it is a parallel connection, right? Now I am connecting them by means of any conducting wire. Now what will happen? Charge will flow from a capacitor which is a higher potential to the capacitor which is at lower potential. Okay, therefore, how long this will continue? This flow of charge, okay, continues till, very important, both till their potential become become equal. Till their potentials become equal. Till then, there will be a flow of charge. Okay, so that equal potential, okay, of the two capacitors, that is what is called common potential. That is called common potential. Are you following? See, before connecting, they were having different potentials. After connecting, charge is shared here. Sharing of charge is taking place. What is the charge flows from a capacitor which is at higher potential to a capacitor which is at lower potential. This happens till both the potential, both will become, both their potentials become equal. Therefore, that equal potential now is what is called common potential. I think you are following. Here, what is that common potential? Here there is no loss of charge, net loss of charge. What is that? Only charge is being shared. Okay. Therefore, the sharing of charges between the two capacitors is taking place. Okay, right. Now, shall we go? Now, our job is to find out the expression for the common potential. Okay, now I told you they are connected in parallel. Therefore, what is the total charge before sharing? Total charge of both the capacitors. Okay, total charge stored in both the capacitors. Okay, before sharing. before sharing. Sharing means what is that? Before connecting parallel. They are separate. Now is yet to connect. Okay, yet to be connected. So before sharing, what is they are individually, they are C1 and C2. There is no connection between them. That time what will be the total charge of both the capacitors stored? Okay, therefore that is given by total charge stored in both the capacitors before sharing is given by what is the first capacitor? What is the charge? CV na, for C1 V1. Next one C2 V2. Are you following? This is the total charge stored in both the capacitors before sharing. Okay. Now after sharing, what will happen? The charge, what is the charge from the capacitor which is at a higher potential? Okay, it flows to the capacitor which is at lower potential. Correct? Till both the potentials become the same. Okay, after sharing. Okay, therefore let you can say V is a common potential. Okay, potential on sharing the charges. On sharing the charges. Okay, therefore can you tell me, therefore now what is the charge? Now what is the total charge? Therefore total charge stored, okay, after sharing. After sharing. Okay, that is nothing but, you tell me what is that? Now they are in parallel. Now parallel connection means what is the capacitance? C1 plus C2. Correct? Okay, and what is the potential here? Capital V. That is common potential. Okay, therefore now, but here on sharing, now what is that? Is there any net loss in charge? No, there's no loss of charge, but only it is being shared from one to another. Therefore I think I can say equation 1 is equal to 2. Okay, therefore what is the equating 1 and 2? That is the same, equating 1 and 2. Why? Because there is no what is that? There is no no loss of charge because of sharing. Okay, therefore I'll take that equation 1 and 2. I can equate. Okay, therefore C1, you can say that what is that? C1 plus C2 into V is equation number 2. That is equal to C1 V1 plus C2 V2. Fine. Therefore, what is the expression for common potential? Therefore, let me go to the next one. Okay. Therefore, what is a common potential? Common potential here is V. Therefore, I can say V, that is equal to C1 V1 plus C2 V2 divided by C1 plus C2. Okay, therefore this is the expression for common potential. This is the expression for common potential. Okay, therefore you can say that common potential is nothing but C1 V1 plus C2 V2. What is that? It is a total charge stored by both the capacitors. Therefore, total charge stored by both the capacitors divided by total capacitance or total capacity, whatever is that. Everything is total capacity. Capacity, capacitance, purposely capacitance, capacity, everything is same. Okay, right. Okay, now is it clear? Now let me go for with this. Let this be equation 3. Okay, so now from 3 yeah, you can say that, okay, C1 V1, okay, plus C2 V2 is equal to C1V plus C2V, correct? Okay, therefore you can say that C1V1 minus C1V, that is equal to C2V minus C2V2. What do you understand by this? See, this is C1V1 is the initial, the charge stored by the first capacitor before sharing. Okay, and what is C1V? C1V, what is it? It is a charge stored by the capacitor, first capacitor after sharing. Okay, therefore, now what is this? That should be equal to, okay, C2V minus, this is charge stored by the second capacitor after sharing, and therefore, which means that from this, what do you understand? This is by second capacitor before sharing. So from this you can say, which is in the left side, the here, this one, it is, you can say that it is the charge, okay, lost by, okay, one capacitor, first capacitor, correct? C1, why? Because initial capacitance is more minus, what is it? It is a initial, what is a charge? Initial charge C1V1 minus C1V, which means that, okay, this is the, it is before sharing and this is after sharing. Therefore, this minus this means what is a charge lost by the first capacitor. But here, after sharing is more than before sharing. Therefore, you can say after sharing is more than before sharing means it is gained. Charge is gained. Na? Therefore, charge gained by second capacitor. Are you following? So very important. What is that? If one, when you are, what is that? You're connecting it, when there are two capacitors are connected in parallel, what happens? That is a, what is a sharing of charge? Okay, how? Is such that, what is that? One capacitor is losing the charge and the other capacitor is gaining the charge. Therefore, there is no loss of charge as such. One is losing, the other one will be gaining. That's it. Hope you're following. But there is no loss of charge. Very important. Okay. There is no loss of, no net loss. You can say. There is no, first capacitor is losing, second capacitor is gaining. But you can say that when they are connected in series, what is it? When the two capacitors are connected in parallel here, in this case, okay, therefore what is that? There is no net loss in the charge. Okay, therefore because of sharing there is no net loss in the charge. One is gaining, the other is losing. That's it. Okay, that is enough. Now shall we go for the next, if they are connected in series, then what will happen? See, I just know this derivation is not required. Just for problem sake, if it is asked, I will give you what is the common potential. That's enough. Common potential will be when the capacitors are connected in series. Not sorry, it is parallel is over. In series, okay, parallel, we have seen parallel only. That is why total, what is that? Charge is equal, what a total capacitance C1 plus C2, no? Total capacitance is C1 plus C2 means what is that? It is a total potential. Total capacitance C1 plus C2 means it is connected in parallel, right? But if it is in series, then what will be? I'll give you the result, that is enough. What is common potential V? That is equal to, okay, C1 V1 minus C2 V2 divided by C1 plus C2. Okay, C1 V1 minus C2 V2 divided by C1 plus C2. That's enough for that. this one. Okay, with respect to parallel combination, we will see everything. Here we have seen that one. Okay, it is in series means this is the common potential. This is the common potential. Okay, now next very important topic is loss of energy on sharing charges. Okay, when due to sharing there is no loss of charge. Loss of charge. So far I think what is that? Charge lost by one capacitor is charge gained by first one capacitor is nothing but charge gained by the second capacitor. That's all. But there is no net loss of charge. Okay. When both are put together, the charge should be is the same only. There is no, as such, there is no loss of charge, net loss in the charge due to sharing. But now we are going to see when the two capacitors are connected to, okay, what happens? There is no loss of charge on sharing, but there is some loss of energy. Loss of energy on sharing the charges. On sharing charges. Now we are going to see what is the expression. See, when they are connected, two capacitors are connected, though there is no loss in the charge, but there is some loss of energy. How? When you are connecting two capacitors, immediately what will happen? There will be some energy will be dissipated in the form of heat. Okay, or sometimes there may be slight spark, light energy, heat energy usually. Okay, heat or light, whatever is electromagnetic energy. Okay, therefore what is that? That is why some energy is lost. All of a sudden when you are connecting two capacitors, okay, there may be some energy that is dissipated in the form of heat, light, etc. Okay, so light means what is that? You cannot say that. Spark, slight spark will be there. Okay, therefore now what is the expression for that we are going to see. Okay, expression for the loss of energy. Right, now where shall we go for when two capacitors are connected in parallel. Now with respect to parallel only, series just a result is given. Okay, when they are connected in parallel, what is a common potential? Common potential V. It is parallel. Okay, common potential we do only with respect to parallel combination, all these derivations. Okay, common potential V, that is equal, it is a continuous, C is equal to C1 V1 plus C2 V2 divided by C1 plus C2. Correct? This already we have seen the same, the result we are taking here. Okay, common potential V is equal to this. Right, now what I want is, okay, total energy before sharing. Now it is, previously we have taken what is the total charge na? Total charge before sharing, after sharing. Now it is what is the total energy before sharing charge. See what is that? Now we are going to see total energy before sharing charges. Before connecting. Once they connected, what happens? There will be sharing of charge. Both the capacitors are connected. Okay, because of the what is that? From higher to lower potential charge will flow. Okay, but before connecting, there won't be, what is it? Therefore, that is why before sharing the charges. Okay, therefore that is let it be U1. Okay, what is that? You tell me. First capacitor is having energy half C1 V1 squared, and the second capacitor half C2 V2 squared. Here I am taking only CV combination. Why? Everything here in CV. That's why. Okay. So which combination to be taken? That depends. Okay. Therefore here it is C1 V1 squared plus half C2 V2 squared. Okay. Next one. Therefore total energy. Okay. What is it? After sharing charge. Now next one. Okay, let that be U2. What is it? That is total energy is nothing but half. When they are connected in parallel, what is the total capacity? C1 plus C2 now? C1 plus C2, okay, into what is the potential? Common potential is V squared. Hope you are following this. This is before sharing total energy and this is after sharing. What is the total energy? Are you following? Therefore, that can be written, that is U2 can be written as, it is not capital, small u is meant for the density, energy density. Therefore, U2 that is equal to half into C1 plus C2 into V squared. V squared क्या होता है इसमें? C1 V1 plus C2 V2, okay, divided by C1 plus C2 V, okay, common potential, the whole squared. The whole squared. Are you following? Okay, therefore, now what you have to do, what is the loss of energy on sharing charges? So now if it is losing the energy because of sharing, okay, what happens? U1 should be more than U2. Why? Because after sharing, energy will be less. Why? Some of the energy is lost in the form of light or heat. Therefore, what is that? U1 should be more than U2. So, how to prove? If you find U1 minus U2, if you find U1 minus U2, the final result comes as positive. Okay, then U1 is more than U2, no? U1 is more than U2. So, U1 is more than U2 means definitely what you can say that, what that is, some energy is lost. If U1 is equal to U2 means, what is that? There is no loss of energy. Are you following? Now, that is the reason. Now, we are going to see U1 minus U2. So, just to conclude that, yes, there is some loss of energy because of what is the sharing of charges. Okay. Now, how to find U1? Therefore, U1 minus U2 you are finding. Why? Just to conclude whether that is energy loss. Okay. Right. That is equal to half C1 V1 squared plus half C2 V2 squared, correct? Minus C1 V1 plus C2 V2 C2 V2 the whole squared divided by C1 plus C2 the whole squared. Okay, therefore, now what you have to do? Okay, minus U2 into half C1 plus C2. Half C1 plus C2. Okay, therefore, you will be having this one, that is nothing but this will go. Therefore, you will be getting half C1 V1 squared plus half C2 V2 squared minus, okay, C1 V1 plus C2 V2 the whole squared divided by 2. Here 2 is there, 2 C1 plus C2. 2 C1 plus C2. Hope you are following. Okay. Therefore, it is half C1 plus C2 V squared. Correct? Therefore, is it clear? It is V half C1 plus C2 total common potential squared. Okay. Right. Therefore, now can you give me what is this? So, you have to expand that. So, it is not a very big this one. Therefore, what is that? U1 minus U2. Therefore, U1 minus U2 that is equal to half. Okay, I think you can take a LCM now. Okay, if you take LCM, I think directly I can do now. Okay, therefore what is that? LCM, let me say 2 into C1 plus C2. You take LCM. Okay, therefore what is that here? You tell me. This is 2C1 plus C1 V1 squared, C1 V1 squared into C1 plus C2, correct? Then okay, and next one, C2 V2 squared plus C2 V2 squared into C1 plus C2. Hope you are following. I am taking LCM, that's all. It's not a very big this one. Okay, minus C1 V1 plus C2 V2 the whole square, and therefore can I do this one? That is minus C1 V1. Therefore C1 squared V1 squared minus C2 squared. Hope you are following, ma. I am just expanding. Okay, A plus B the whole squared. Okay, therefore minus C1 squared V1 squared plus minus, because the minus is there, no, here minus, this is minus, therefore minus C2 squared V2 squared, it is C2 squared V2 squared minus, okay, 2 C1 C2 V1 V2. Are you following? Okay, what is A plus B? A plus B, C1 V1 plus C2 V2 the whole squared is nothing but what is that? C1 squared V1 squared plus C2 squared V2 squared plus 2 C1 C2 V1 V2. But minus sign is outside, therefore what is that? Everything here, right? Therefore I think that is nothing but even I think this can be written as C1 squared V1 squared plus C1 C2 V1 squared, okay, plus, okay, here C1 C2 V2 squared. I am expanding, I am not doing very, okay, plus C2 squared V2 squared, okay, minus this one now, C1 squared V1 squared minus C2 squared V2 squared minus क्या है 2 C1 C2 V1 V2 divided by 2 into C1 plus C2. Okay, right? Therefore, there are so many factors cancelling. You see, C1 squared V1 squared minus C2 squared V2 squared, that will also cancel. Therefore, U1 minus U2 you will be left with. इसमें C1 C2 है, इसमें C1 C2 है. What are all the which is not cancelled? You see, everywhere C1 C2 is common now. Therefore, I think I can take C1 C2 common. C1 C2 common लेने से, therefore what am I doing? We're getting here V1 squared, correct? Plus V2 squared minus, so minus, okay, 2 V1 V2 divided by 2 into C1 plus C2. Okay, therefore what is that? That is nothing but C1 C2, okay, into V1 minus V2 the whole square है ना, A plus B, A minus B the whole square ना, A square plus B square minus 2AB, like that in the formula. Okay, V1 minus V2 the whole square divided by 2 into C1 plus C2 है ना, 2 into C1 plus C2. That is nothing but your U1 minus U2. What do you see? The result says, okay, here C1 C2 capacitance always positive. Okay, therefore C1 C2 by 2 into C1 plus C2 into V1 minus V2 the whole square हो जाएगा. Therefore definitely it has to be positive. Definitely this quantity has to be, okay, which is positive. So which means that U1 minus U2 is positive, means therefore you can say U1 is more than U2. Okay, that confirms that. This confirms what? This confirms that there is a loss of U2. The after sharing is U2, before sharing is U1, right? Total energy. After sharing, the energy is less than the energy before sharing. Therefore, which means that it confirms definitely. What is that? There is, it proves. Therefore, this proves. What it proves? That, okay, the energy, total energy after sharing, total energy after sharing what? After sharing charges. Yes. Okay, less than the total energy before, okay, sharing the charges. Before sharing charges proves that the total energy after sharing charges is, what is that, less than that before sharing. Okay, so this is a very, very important result. Okay, now I think one or two problems we'll see after we go. Okay, I think energy with energy, one problem we'll see. The first problem we'll see only two problems. Okay, right, what is that? Numericals. Number one, let me go for some different colors. Right, okay, see what capacitance is required. See what capacitance is required to store an energy of 100 kilowatt hour. Energy is given in kilowatt hour. Okay, at a potential difference of 10 power 4 volt. 10 power 4. See, what capacitance is required to store an energy of 100 kilowatt hour, okay, at a potential difference of 10 power 4 volt. Okay, you are asked what are all the things given first. Energy is given. Okay, what is energy? Energy that is equal to, let me go for some other color. Some other color. What color? Blue, right? Therefore, what is that? What is given? U, that is equal to 100 kilowatt hour. Kilowatt hour, 1 kilowatt hour is equal to 3.6 in 10 power 6 joules. Na? So first you have to convert into SI unit. Therefore, this is 100 into kilowatt hour. Kilowatt hour is 3.6 into 10 power 6 joule. Okay, 1 kilowatt hour is this, right? Therefore, that is nothing but 3.6 into 10 power 8 joule. Okay, so this is that, what is that energy stored. And what else is, immediately first you have to convert it into the SI unit. That is very important. Therefore, potential difference is given as 10 power 4 volts. Okay, therefore, we are asked for what? Capacitance. What is the capacitance? Therefore, I think you know that how U, C, V all are connected. U, that is equal to half CV squared, na? Half CV squared. Okay. Therefore, what is your what I want is C. C is equal to U by V squared. Okay. What is that? 2U? 2 into 3.6 into 10 power 8 divided by V square. Therefore, V square means 10 power 4 square, 10 power 8. Okay. Therefore, it is nothing but what is the answer? That is equal to 7.2 farad. Huge. 7.2 farad. Are you following? Okay. So, this is the why? Because the energy stored is very high. 3.6 10 power 8 joules. Okay. Potential difference is also very high. Therefore, definitely automatically C is 7.2 farad. Okay, fine. One more question. One more. We'll see problem. What is that? See, second. Okay. What is it? See, simple. 600 picofarad capacitor is charged by 200 volt supply. 200 volt supply. Okay, and it is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. Okay, now what is to be done? Now we have to find out. What is to be found out here is how much energy, electrostatic energy is lost in practice in this process. Okay, in this process. In this process. Okay, what is that? Very simple. See, you have two capacitors, both are 600 picofarad only, but one is initially it is charged. Okay, actually it is potential charged by potential difference of 200 volt initially, but the other one is uncharged. Right? Therefore, what will happen? One is charged, other one is uncharged. Therefore, one is at higher potential 200 volt, another is uncharged, means zero potential. Correct? Therefore, what will happen? There will be the sharing of charge will happen. Once there is a sharing of charge, they are connected and connected to another uncharged 600 picofarad. How is connected? Parallel only you have to take here. Okay, see, we have seen only so far nothing is given, means they are connected in parallel. Okay, therefore they are connected in parallel. Therefore, because we have seen everything with respect to parallel connections only. So what is that? Therefore, once they are connected, there will be sharing of charge. Because of that, there will be some energy lost. Okay, so very easy now. What is C1? Both are of same capacity. Therefore, that is equal to 600 picofarad. Pico means 10 power minus 12 farad. Okay, right. Now, what is V1 initial capacity? E1 is equal to 200 volt. Okay, but V2 is uncharged. Uncharged means what is that? V2 is equal to 0. V2 is equal to 0. That's it. Now, you have to go for direct substitution. What is the energy lost? Formula क्या होता है? Energy lost, that is equal to, what is the C1, C2? Here just now we have seen now. See, what is that? Energy lost is C1, C2 into V1 minus V2 the whole square divided by C1 plus C2. This formula you have to use. Okay, therefore now you come here. Okay, therefore energy lost, that is equal to C1, C2 into V1 minus V2 the whole square divided by 2 into C1 plus C2. Okay, that is equal to 6 into 600 10 power minus 12. Therefore, I can write 6 into 10 power minus 10. Correct? C1. C2 6 into 10 power minus 10. Okay. V1 minus V2. V2 is 0. Therefore, you can say 200 into V2 0 means 200 the whole square. Okay. Divided by, what is it? 2 into this one. Okay. 2 into C1 C2. What is C1 plus C2? 2 into 12 into 10 power minus minus 10. Correct? Okay, therefore, when you calculate everything, so many things are cancelling. Okay, so you will be getting the final answer as 6 into 10 power minus 6 joule. This is the expression for energy lost. Energy lost is, okay, so it is 6 into 10 power minus 6 joule. Is it clear? Okay, that is it for today.